Welcome to Unit 4. We look at lines and planes and distances between lines and planes. And we have already talked about planes last time, and we had a prototype problem like finding the plane through 3 points. Let's take 3 points. B is equal to 3, 1, 2, and C is equal to 5, 2, 3. So what we have learned is that the vectors are very useful here. We can take this vector from AB. So this vector, let's call this V. So V is equal to AB. That's the vector which has the components 2, 1, 2. And then we have another vector here from to AC. This vector is W. In this case it's 4, 2, 3. And then came the cross product. What was important is the cross product is a vector here perpendicular to V and W. Let's call it N. And I also will generically always denote it with ABC. And so we have learned last time that this is perpendicular to these vectors. So it is perpendicular to the whole plane, right? There's a whole plane here which passes through this point A and contains these vectors V and W. Now, how do we get the equation of the plane? Equation of the plane was ax plus by plus cz is equal to constant, and so for that we had to compute the cross product of v cross w. Let's do that here. V cross w is, let me just do it as I did the last time. So I write it as column vectors. Maybe it's a little bit easier to do. You can also leave it as row vectors, and so we have that cross product here. And then what I did last time is I just copy the first two entries again, and then I do this cross multiplication here, right? I got this 3 minus 4 is minus 1, 8 minus 6 is 2, so this is minus 1, 2, and here we get 4 minus 4 is equal to 0. So we get this vector v cross w, which we call ABC, and then we can write down the equation directly. We can write down the equation of the plane, which is the plane has the form ax plus by plus cz is equal to d, and in this case it is just minus x plus 2b is equal to constant, and the constant we can get by plugging in the point, like for example 1, 0, 0, which is equal to minus 1. So that's the equation. That's the equation of the plane. Now I want to add something here, because we also talk about lines where we have no more just an equation, but we parametrize it. We can also parametrize this equation, and this is called a parametrization of the so S and T. We have two parameters, and I can just write here, I just can write OA plus S times V plus T times W. So this is called a parametrization. Let me just write down what this actually means. This means the coordinates, the components x, y, z is the vector, maybe from here, from 0 to A is 1, 0, 0. And then we take S is a constant, so a parameter which we can vary. So it's not a constant, it's a parameter, and S times the vector V, which is 2, 1, 2, and then plus T times the vector 4, 2, 3. And so I can write that in one term if I want. I can write that as 1 plus 2s plus 4t. I can write that as s plus 2t, and I can write this as 2s plus 3t. So you see this vector x, y, z, which is on the plane here, it's just s times the vector v plus t times another vector. So this is if this is s times v and this is t times w, what we have here is x, y, z. So that's a point x, y, z, or a vector x, y, z. If you write it as a vector, this vector x, y, z can be written as a combination of these vectors v and w, but we have to add the point a so that we are on the plane. So this is called the parametrization of the plane. So there are many parametrizations. It's not unique. Also here, this is not unique. We can multiply this by 5, for example. We get also another equation. So these are the two things. These are the two possibilities to describe planes. Okay. In the second section, we look at lines. Lines are defined by 2 points. So here we have a point A and a point B. So the line is infinite. It goes through A, goes through B. And now we cannot describe this with one equation. We would have to use 2 equations, 2 planes intersecting 2 planes. We will see that in a second. But what we can do is we can parameterize. As we have parameterized the plane, we can now also parameterize this line. And it's even easier because what we can say is we can say a general point on this line has the form. We start with 1, 0, 0, and then we take t times the vector v, which in this case was just 2, 1, 2. So what we call this is a parametrization of the line. Let me just write down in general how we write this. We say r of t, and then we have OA. A is a point on the line, and then plus t times the vector v. V is the vector inside the line. So that's the parametrization of a line. And if we wanted to write equations, we could do that, but it's not so convenient. We can actually just take these equations here and say x is equal to 1 plus 2t, y is equal to t, and z is equal to 2t. And now we can eliminate t, right? And what we get if we eliminate t, we say t is equal to x minus 1/2. That's t from the first equation. That's also that's also y, right? So we solve for t in each case. And in this case we have t is equal to z/2. So these are also called the symmetric equations. And so this is the intersection of two planes, a plane and then intersect with a plane y minus z/2 is equal to 0. Or we can say that. So we have 2 planes. We can take these 2 planes, we can intersect them, and we get that. But that's not so important, these symmetric equations. What is much more important is the parametrization of the line. This gives us a real kind of a picture. We can draw it. The computer can say, okay, for t equal to 0, we are here. For t equal to 1, we are here. For t equal to minus 1, we are here. So think about t as time. That's all what I wanted to say about lines. And next, what we do next is compute some distances. Okay, so if I have given a plane and I have given a point, we want to find the distance between the point and the plane. And what happens is of this distance is that the point connection from the point to the plane, this we mean the shortest connection here. So this has to be perpendicular to it, and that's why the normal vector is very important. So let's take this plane which we have already seen here, which has the normal vector 1, minus 1, 2, 0. So that was this normal vector, and so the plane was given as an equation, right? The plane was given as minus x plus 2y is equal to minus 1, and it contained also a point. The point was just 1, 0, 0. That's the point A is equal to 1, 0, 0. Now, what we can do, let's just also call it, in general, I also call it Q here, a generic point on the thing. This another thing what we have is a point P, which is maybe I take the point 4, 4, 4. So I just drew the normal vector here through that point P, but the problem is to find the distance between this point 4, 4, 4 and that plane. So so I have already the picture here, which gives us the formula. What we do is we take this connecting vector here, QP, that's a key, and what we do is, in order to get the distance, what we can do is we can project it onto that. So this is the projection. We talked about the projection here, and it's the length of this projection. And so what we can do is we have the formula for that. We can say we project PQ onto N and take the length. So this gives us the distance is equal to PQ times N over N. So that was we had it also times N over N absolute value, magnitude, and so that was that's the distance. So that's the distance formula, and so that's one way also how can you remember. You can remember it. It's a projection, and there's another way. Kind of if these vectors v and w would have been given here, kind of v and w on the plane, we can also write this as v cross w times n, so times pq over v cross w. And we usually should take the absolute value here, because this also can become negative and the distance should be something positive. This we will interpret just in a second as we can see this as volume over area, volume of a parallelepiped over area. That's another way to see that distance formula. We have already talked about volume last time, and we have talked about area also in unit 3. So this is also volume over area, which is the height. And but for now, I think it's nice to have also seen that projection is important. That's the first distance formula. We discuss now the distance from a point to a line. So here, and again, kind of if you have a line given in the point, what happens is that we mean the shortest connection which goes from the line to the point. So that has to be perpendicular, right? Shortest means if it's not the 90 degrees, we can make it shorter here. We can go straight down, and by Pythagoras we have something smaller. So what we again want here is a formula, and let me just draw this line again, this vector again, this vector PQ. Now, one way how we can see this is using that angle here, alpha. You see that this distance is actually just PQ, length of PQ times sinus of alpha. But we don't like trig functions here in the computation, so it is kind of useful to multiply this with v and divide with v also. So what we do is we make a little trick here. So we have multiplied and divided by the same thing. This is a non-zero vector here. And what we get is a nice formula we have actually seen. This is the length of PQ cross V. And then we divide by the length of V. So that's the distance formula which we are interested in. And this distance formula, again, doesn't use any angle alpha. So this is the distance between a point and a line. So let's just see what we actually get here in this case, PQ. So in the case of the, I actually realize I have not done it in the case computed in the case numerically in the case of point plane here. So in this case, let's just do that here. PQ is the vector 3, 4, 4. So we have now to take the cross product of 3, 4, 4. We cross it with a vector v, which is 2, 1, 2. 3, 4, 2, 1. 8 minus 4 is equal to 4. 8 minus 6 is equal to 2. And 3 minus 8 is minus 5. And then we have that length, the length. So in this case, it would be 16 plus 4 plus 25. Square root, which is equal to 45, the square root of 45, and then divided by the length of v. The length of v has 4 plus 4 plus 1 is divided by 3. So the length of v is equal to 3. So actually we can simplify that even a little bit more. That's actually just the square root of 5 divided by 9, the square root of 5. So I think that's the distance here. I just realized we have not computed the distance here in this case. We had the point here 4, 4, 4, and the distance between, let me just put that here, the distance between, let's call this P, and the plane, that's the plane. So let's call this sigma, this plane here, and this distance here we have not yet computed. In this case, the distance formula was PQ times n over n, and in this case PQ is this 3, 4, 4 times n is minus 3. When I take 3, 4, 4 times this, I get minus 3 plus 8 is 5. So this is 5 over n square root of 5. Oh, that's so funny. We get the same. We get the same. We get the same distance for the point plane. Good, but in this section we have discussed the distance between a point and a line. And also this you can see geometrically as an area of a parallelogram. So it's actually an area of a parallelogram here. So this is also area divided by base length. So this is also a height. So you can see this height here of the parallelogram is just the area divided by the base length. So there's no need to learn these formulas by heart. You can always just think about what it actually does, what does it mean. And I like these formulas because everything comes together. Cross product, dot product, length, projection, area, volume, everything comes here in. Cool. The last thing is the distance between two lines. Okay, in this last section 5, we look at the distance between two lines. That's the trickiest thing, but also this can be explained geometrically quite well. But let me just give you the picture. So what we have two lines in space. They in general don't intersect. It's very special if they intersect. But what we want to do is we want to find the distance, the shortest distance between these two lines. Now what happens is this shortest distance again has to have the property that it has to be perpendicular to both. Right? If it's not perpendicular to one of them, we can make it shorter by just going directly towards it. So that's an important principle. It has to be perpendicular. So if this line contains the vector w and this line contains the vector v, what is important is v cross w. And that's what we have here. Kind of if we do that, v cross w is something perpendicular to it. And let me just actually just draw it here somewhere. Kind of this is n. So n is equal to v cross, that's actually a different w than here. So in this case we have a different w here, but we can quickly compute that. So this is the cross product of 2, 1, 2 and 1 minus 2 minus 1. So I just do that again, 1, 2, and I get 1 minus 1 plus 4 minus 1 plus 4 is 5, 2 plus 2 is 4, and 4 minus 1 is 3. So that's the vector perpendicular to it. So in this case we have a different problem, right? The p was before a point which had the distance to the plane. In this case we just take this as this p and this point c as our points for another line. So what we have given is, we have given 2 points, maybe A, maybe Q and P, and we have given 2 vectors, V and W, and this defines as 2 lines, and we want to find the distance between them. Now there are 2 ways to look at it. So one way to look at it again is to project the PQ onto N. So the distance which we can do is we can see, but that's harder to see why this is true. So this is just PQ times N over N. Which is exactly the same formula like for the distance between a point and a plane. So this is again just by seeing a projection as a projection. But it's not so, you see, you have to kind of see that you take this vector and project it here onto that. So you have to translate first a little bit and then project it. So that's one way to see this. But what we can also do is we can see it as this is the same thing, because n is equal to v cross w and over n. And actually for n, instead of n, I write again v cross w here. And what we can think about is, again, this is volume over area. So what we can do is we can, I will explain this in class a little bit better. If you have these 2 lines, we can form a parallelepiped which is built like that. So what we do is we have here this connection PQ. This doesn't have to be perpendicular, right? And so these are the 2 lines. What we can do is we can go down here, build one plane, or we can go up and build another plane. These planes are parallel. And what we have is this also forms a parallelepiped. And what we have is actually just the distance between these 2 planes. So the distance between these 2 planes, these 2 tablets, this distance between these 2 planes is exactly the distance between the 2 lines. So one line contains this in one plane, and one line is in the other plane. And so the distance between these 2 lines is actually the distance between these 2 planes. And so what we do is we build a parallelepiped, and the height of that parallelepiped, which has a bottom and a top, is just the distance. And that's what we compute here. So also again, there is no need to learn this by heart. It's a volume over an area. And also again, these distance formulas are fantastic, because if you understand them, you understand the whole week. You understand vectors, you understand points, you understand cross product, dot product, area, projection, volume. Everything comes together here.